Is audio isn't working?
Something's wrong with the sound.
Is it the video or is it?
Yeah.
Since he's here, you could say we talk live.
Yeah,
Oh,
maybe
hi.
Fabian, I see you are online. We have some issues with the sound of your video.
Maybe it's not.
So we give it one more try. Would it be an option to? Do you have the slides on your computer?
I do.
Okay, so what do you think? Can it work?
It's a possibility, but we had few videos in the previous session and it was working perfectly. So something's wrong from the video.
Okay. So could we set up like a
I think
screen
we-
share?
Presenting the Iterative SE3 transformer, a graph neural network which respects rotational and translational symmetries. I'm Fabian, and my collaborators are at Wagstaff and Ingmar Posner from the University of Oxford, as well as Justas Dauparas from the University of Washington. Our work is primarily motivated by applications in the analysis of large molecules, and in particular in modeling and predicting the structure of proteins. Malfunctioning proteins are responsible for a wide range of diseases. Often, we want to find a drug such as a small molecule that can bind to a specific protein and inhibit it. Finding suitable small molecules is a lot easier if you know the precise structure of the protein. Often, you can determine the structure through experiments, for example with X-ray crystallography or cryo-EM. However, that can be an extremely difficult task. There are examples where people took 30 years to determine the structure of a single protein. Bottom line, if you manage to develop a computational method that can accurately predict structure, that would have a huge positive impact. What you see here is an example of a recent model doing protein structure prediction very successfully and accurately. The pink arrows show that the authors used an SE3 transformer in 2 places. There are also a lot of other things happening, like multiple sequence alignment, but for the purpose of this talk, we'll consider a simplified version of protein folding, where we take as input a chain of atoms and output the folded protein with all the atoms in their correct final positions. This simplified problem, in common with other molecular analysis applications, has 2 properties that can usefully be incorporated into a machine learning model. The first property is rotation and translation equivariance. In simple terms, this means that the orientation and position of a molecule are not important to solving the task. This property can be captured in the mathematical specification of a machine learning model by making use of group theory, which is where the technical term equivariance comes from. Depending on your mathematical background, this may or may not sound a bit complicated. For a more intuitive explanation, think about convnets. A single convolutional layer applied to an image is known to be translation equivariant. This means that if we shift the input image a few pixels to the right, the output feature map will also be shifted a few pixels to the right. In a sense, the concept of translation equivariance here gives convolutional neural network models an inductive bias what 2D image coordinates are. Now we are simply extending this concept to translation and rotations in 3D to implant an inductive bias about 3D coordinates into our neural network. The second property is that the behavior of the molecular system can be described by the pairwise interactions between atoms. This means that the data can naturally be described as a graph, where each atom is a node, and the interaction between a pair of atoms can be regarded as an edge joining that pair of atoms. Any information about the interaction can be regarded as information attached to that edge of the graph. The SE3 transformer is a neural network model which was specifically designed to incorporate both of these properties. As we pointed out before, this has been successfully applied along with related models in protein structure prediction problems. In the SE3 transformer, a graph describing a molecule is the input into the model, and a modified graph is produced as output. The SE3 transformer may have many layers internally, and each hidden layer's feature representation consists of features on the same underlying graph. However, crucially, the positions of the nodes in this graph, which is to say the positions of the atoms in our molecule, are held constant until the final output layer. In this sense, the SE3 transformer is a single-pass model. The model only has one chance to update the positions of the atoms. In the context of protein folding, this clearly places a substantial burden on the model. We are asking the model to jump immediately from the input to the correct final protein structure, without considering any intermediate positions of the atoms. The novelty in our work here is that we eliminate the single-pass behavior and produce an iterative model, the Iterative SE3 transformer. We allow the model to update the positions of the nodes multiple times before reaching the final output. In other words, we are giving it the ability to explore the space of configurations of atoms on the way to producing a solution. There are some complications and design decisions involved in introducing this iterative behavior into the model. Probably the most important complication is in the training process. If we train the model end-to-end, the gradient flow in the iterative model is significantly different from that in the single-pass version. This change comes about because of the way in which rotation equivariance is built into the model. Essentially, rotation equivariance is preserved by expressing all of the functions which make up a forward pass of the model in terms of a set of rotation equivariant basis functions. These basis functions are constructed from spherical harmonics, but crucially, they also depend on the relative locations of the atoms. In this single pass case, the atomic positions are fixed, and therefore the basis functions do not change, and the gradients do not flow through them. This point is illustrated in this figure. We see the gradient flow illustrated in orange. The basis functions at the top are represented by a sketch of spherical harmonics, and the learnable parameters of the model are represented by the 3 neural network blocks at the bottom. By contrast, the iterative model does update the relative locations of the atoms, and so gradients must flow through the basis functions. The key point is that gradients flow through anything downstream of a learnable parameter in the computational flow. In the single pass case, the basis functions are not downstream of any learnable parameter, whereas in the iterative case, they are. So what does that mean? It means that we need to backpropagate through the spherical harmonic computation in order to get the gradients. Interestingly, you could train the network without doing that, but there would be an error in the gradients. And that error of the gradients would come from not taking into account the intermediate position changes properly. But the intermediate position updates are really the main aspect that we care about here. So making the basis functions and the spherical harmonics differentiable is conceptually the much nicer way to deal with this. And this is also reflected in the results, as we will see later. Another key consideration for the iterative model is to avoid an information bottleneck between iterations. The internal layers of the SE3 transformer allow for rich hidden feature representations. The definition of these feature representations is complicated by the need to maintain rotation equivariance, but they can be thought of analogously to the hidden features of any neural network. The final output graph, instead of having these rich features, only needs to contain the same kinds of physical information as the input, such as atomic charges and positions. Simply chaining single-pass models together would therefore result in each iteration of the model only receiving a graph poor in features as input. There's a risk of throwing away useful information from the hidden representations between each iteration. To combat this, the iterative model is designed so that the output of each intermediate block also contains additional features, allowing information to be carried from one iteration to the next, avoiding a bottleneck. In this figure, this means that the intermediate graph G1 has more information attached to it than both the input and the final output graph. It is possible to share neural network parameters between the blocks of the iterative SE3 transformer. The model could then be broken down into 3 parts: an input block which maps the graph to a rich intermediate representation, a middle block which repeatedly processes the intermediate representation, refining towards a solution, and an output block which produces the final solution. This has the advantage of allowing a variable number of iterations. However, using weight sharing in this way forces each intermediate iteration to perform exactly the same subtask. Depending on the overall task, the early and late stages of the solution process may look very different, and weight sharing is therefore not appropriate in such cases. Instead, each block can have different weights, allowing for the learning of different subtasks. Our experiments with this model are on a toy physical problem designed to provide a clear illustration of the benefits of the iterative version. We define a physical system where each pair of atoms interacts according to a pairwise potential, and our task is to move the atoms so as to minimize the total energy of the system. This figure shows a system of 5 atoms, and the gradient of the potential between each pair indicated by the color of the edge between them. Blue indicates that the atoms are attracting each other, orange indicates that they are pushing each other away. The exact choice of potential varies from pair to pair, so that the minimum energy is reached at a different distance for each pair. Additionally, the potential is chosen to have a double minimum. This creates a complex energy landscape, which is not trivial to solve by gradient descent on the potential with respect to the atom's positions, allowing for a meaningful baseline comparison. In a sense, the motivation for constructing the example in this way was to create a problem that mimics, at least to some degree, the complex energy landscape of protein folding, while not burning a ton of compute when experimenting with different architectures. We compared the performance of gradient descent, a single-pass SE3 transformer, and an iterative SE3 transformer. Additionally, we evaluated the performance of running the iterative SE3 transformer and then fine-tuning the solution by gradient descent. Gradient descent in itself is a really strong baseline here because it is guaranteed to find a near-perfect local minimum. Therefore, it's also not surprising that gradient descent outperforms the vanilla single-pass SE3 transformer. However, the iterative SE3 transformer outperforms both the single-pass version and even gradient descent. Moreover, the fine-tuned iterative version performed the best overall. The fact that the fine-tuned iterative SE3 transformer outperforms straightforward gradient descent allows us to observe that the model is finding a genuinely different solution to gradient descent, moving the state of the system into a different, deeper gradient descent basin. Thank you so much for your attention. I hope it inspired you to work in this space. I think there are so many interesting theoretical and practical problems to solve. If you follow the link, you will find the paper, our blog post, and our code base. Hello everyone. I will be presenting the iterative SE3 transformer, a graph neural network which respects.
Thank you very much, Fabian. Can you, and Edward is also here, can you unmute yourself and maybe quickly say hi so that we know you're here?
Hi.
Hello.
Okay, both are here. That's great. Are there already questions from the audience? Okay, that's one here by Max.
Hey, Fabian, can you hear me?
I do, yeah.
Hi, great work, thank you. So I wonder if you had time to compare this with the GNN paper that we submitted to ICML, because it seems it's different, but also similar in some sense, right? We also evolve, positions X in a simpler way, I think, because we don't have the full sort of irreducible representations of the rotation group. We just have one vector. But in some sense, we also have a very rich GNN message passing scheme. And I haven't read your paper yet, but I don't know how you, I mean, I guess it's related to your bottleneck problem. So have you been able to somehow compare these two things, even theoretically or experimentally?
Okay, I think the iterative SE3 transformer is really a direct extension of the SE3 transformer. And I think the main difference to E3GNN that I see is that we have these spherical harmonics, and you need to that makes it a little bit more complicated to make it iterative. So I think the main difference are that we need to backpropagate through the spherical harmonics, and how to deal with that. In principle, I think, yes, those are very similar ideas. I guess I never looked at E3GNN from the perspective of like structure refinement, but you can very well do. I mean, that's what we did in the generative version, right? That we also refine structures using a variant of the E3GNN. So I think, yes, they're very related, those ideas. Yeah.
Thank you.
Thank you. I have a question for you regarding the spherical harmonics embeddings. So those are the node features, right? Functions that are like vectors that transform under the Wigner-D matrices. And I was wondering, how do you do the position updates? Do you do this by predicting 3 scalars that sort of move the points around, or do you predict like a first order spherical harmonic vector, let's say, that encodes for this relative position in the update? I was just wondering, is this spherical harmonics concept is used also, well, in these update rules, or is it just for representations?
That's a great question. Yes, it is used for the update rules. So the position updates are type 1 features. So the position updates in themselves are equivariant. So if you rotate the input, then the position updates will rotate as well. And then those new positions, they will then be fed into the computation of the new spherical harmonics of the next block. Yeah.
Okay, thank you very much. Are there any other questions from the audience, maybe? Maybe one last question regarding active non-linearities in the network. So how do you deal with that in this particular type of network where you have node features that are spherical harmonic? So I think of them as a Fourier basis on the sphere, right? And applying non-linearities in the Fourier domain is quite unusual. So I was wondering, what are you doing there?
So yes, if you would, I think what you're referring to is if you applied non-linearities to each kind of like number individually, then you would break the equivariance. Do I understand you correctly?
Yeah.
But what you can do is you can take let's say a type 2 feature, which is 5-dimensional, and compute the norm and then manipulate the norm.
Is that what you do, or is the attention enough in this case?
We do that. Yes. I'm wondering whether we do something more complicated as well. So what you could also do is you could take the scalar product of 2 features of the same type, so like 2 type 2 features, and then use that to rescale another type 2 feature. But essentially, we're always manipulating the norm, and we try different ways of doing that. Not sure off the top of my head which one is the one used in the experiments.
Okay, thank you very much. Yeah, there's plenty of research going in this direction. Was just curious how you dealt with this. But thank you very much for your answer. If there are no other questions, seems not at the moment. And thank you very much, both Fabian and Chris.
Thank you for having me.
So the next talk will be by Leonardo Gigli. He's available here and in the room. So please set up. Leonardo is a researcher at